merging memory and computation is very, very critical to what we're doing. And it's actually the basic physics argument coming out of this that not only predicts that this project is timely, it predicts that it's actually realistic, and we actually think we have a right approach for making this happen. So we talk about merging data and computation. This is what this actually means in practice. So this is obviously a very high-level cartoon of how biological computation works. So you've got a neuron, you've got some set of neurons that's feeding into it, you've got then the axon coming out, its signal to some other set of neurons. So there are two absolutely critical things here. First, convergence, pointed out down here. To get any sort of activity or any level of any firing activity coming out of this neuron, you need coincident activation from multiple input sites. So in this case, say for example, 2 out of 3 input neurons might have to fire to trigger a decision here. So an output signal coming from this neuron. And the other critical point is that every single part of the system is stable. So that's really where the merging data and computation comes in. So each one of these arrows, you're going to have some number of synapses and junctions that are connecting the presynaptic and postsynaptic cell. And each one of those synapses has actually a very, very large amount of state. So every time one of these decision signals is flowing down an axon and flowing to an adjacent neuron, it's not just an information transferal, it's an information transform. You've got memory and computation existing in the same physical space, in the same hardware. You've got information continually flowing through the entire system and transforming as it goes. So if you were to break apart a brain, you could not say this chunk of brain has memory in it, this chunk of brain has computation in it, and then there's some amount of data traffic between those. It's all post-autonomous and all continually. So then if you actually want to go and say what these things actually look like. So we've got a very beautiful slide of biology, some very clever genetics to make this work, but it looks like a big organic mess, obviously. Whereas if you look at a microprocessor, you've got, even though this is a fairly high-level macro-scale picture, you're looking at things that look kind of like regular organized engineering structure. So you've got memory down here, you've got cores here, which are the processing units, you've got a queue here,
to be to go